All right, let's go ahead and continue our discussion of eigenvalues and eigenvectors, and we'll get into diagonalization today as well. And diagonalization will be the last topic that we talk about this semester, which is probably a good thing. So, all right. So last time we talked about, or at least we reminded ourselves of what eigenvalues and eigenvectors are, and what the characteristic polynomial is, what the characteristic equation is, and we've already talked about how to solve this. So let's do one of these by hand here real quick. I'll show you how we can use the calculator to help us find some of these. And then we'll do some diagonalization examples. So this is the matrix that we had at the beginning of class, or whenever we started talking about it yesterday, or Monday, I mean. This is the matrix we had. We already discovered that we had eigenvalues, I believe, of 1, 2, and 3. And the eigenvectors already there. So let's talk about how we can solve this. How we would solve this if we were actually trying to find those things as opposed to me giving you the eigenvectors to start with. So again, the idea here is that we're going to calculate this determinant and we're going to set it equal to 0 because that's going to give us those non-trivial solutions to the homogeneous system. That'll find the eigenvalues. To find the eigenvectors, we'll plug those back in to the matrix where we've subtracted lambda off the diagonal, row reduce, and figure out a basis basically for the kernel or for the solution set there. If you think about transformation ideas, it's like the kernel, right? It's the solving that homogeneous system. So here, if we do the A minus lambda I, again, that just has the effect of subtracting lambda off the diagonal. Because again, this is lambda times the identity matrix, so this is just a diagonal matrix that has lambda down the diagonal. And when I subtract, that just has the effect of subtracting lambda off the diagonal. To find the characteristic polynomial, we want to take the determinant of this matrix and as a nice little review idea, remember when we do determinants, we can expand. If we want to do expansion by minors, we can expand along any column, we can expand along any row, and we like to pick columns or rows that have lots of what's in them. Zeros. Which column or row might you use in this case? Yeah, column 2, right? I've got 2 zeros there and only 1 non-zero term there. So when we expand, 1 minus lambda will be our coefficient, right? What's left? What's the minor associated with it? 4 minus lambda 1. Negative 2 and 1 minus lambda. The other thing that we need to worry about, of course, is it positive or is it negative here, right? So that's positive, negative, positive, negative, positive, negative, right? Remember we start with a plus in the upper left-hand corner. Alternate across, alternate down, right? In particular, anything on the diagonal is always a plus coefficient. So far, so good. Now we've got a 2 by 2. We would have 4 minus lambda times 1. Oops, forgot my 1 minus lambda out in front. 1 minus lambda times 4 minus lambda times 1 minus lambda. Minus a minus makes a plus a 2 for that determinant. Again, our goal here is to find the eigenvalues. To find the eigenvalues, we set this determinant equal to 0. If we've got a polynomial that we want to factor, we'll have a polynomial, we want to factor it, then to find its zeros. Since I want to factor it, and I already have this factor sitting on here, I don't want to distribute this through, is what I'm saying, right? However, we do want to try to factor the other part. I do need to multiply it out and then refactor Here we get lambda squared. We'll get a minus 5 lambda. Plus 4 plus 2 gives me a plus 6. And that does refactor as lambda minus 2 and lambda minus 3. Again, this is the characteristic polynomial. This is going to be a polynomial in lambda. Notice that we've got a 3 by 3 matrix here. What's the highest power of lambda we're going to see? 3, right? And that's always going to happen. So if you have an n by n matrix, its characteristic polynomial will always have degree n. So we would expect n roots, because it is an nth degree polynomial. They may be repeated. They could be complex. We could get complex eigenvalues. If you're in DBQ, you've probably seen complex eigenvalues, maybe. When you're solving some systems of linear differential equations. Yeah. Okay. So it's possible to get complex eigenvalues. Good news is that I'm not going to do those. Okay. The eigenvalues and eigenvectors you'll be getting for me will all be reals, so you don't have to worry about that. However, complex eigenvalues are a thing, and they have applications. Okay, just so that you're aware. All right. In any event, this is your characteristic polynomial. It just happens to be factored as well. Okay, but we could see if we multiply that out, we would get a degree 3 polynomial. In this case, we've got 3 distinct roots. When I set it equal to 0, we can see those roots are 1, 2, and 3, which is what we came up with in the example we did last time, right? So in this case, if you're actually going to find them, you would set this equal to 0. So you'd have the 1 minus lambda times lambda minus 2 times lambda minus 3 equals 0. Lambdas 1, 2, and 3. Those would give you your lambdas. Of course, you can probably see that the bigger the matrix gets, the more complicated it could be to find these particular zeros of the characteristic polynomial, right? So you're probably going to want to use a computational aid to be able to help you do that. Well, a lot of computer programs have eigenvalue packages built into them. We've played with R some this semester. R has them built in there as well. But let me show you how you can kind of force the calculator to help you. Okay, it has to be a little tricky. There's not an eigenvalue function on your calculator. However, there is a graph. This is a graphing calculator, right? And there are ways to find the zeros of graphs with your calculator. So what we're going to do is we're going to graph the characteristic polynomial without computing it, and then let the calculator figure out where the roots are. Okay. So to do that, I'm going to clear this out. Let's go up into our function menu. So go up into the y equals menu. I'm just going to graph the determinant of. So remember, you get your characteristic polynomial by doing a minus lambda I, right? To get the graph on here, I'm just going to replace the lambda with an x. There is a command for the I in here, the identity of whatever the size of the matrix you want. And then, of course, we know how to do matrices. So this is the command, what the command's going to look like that I'm going to put in this function, all right? So when I'm in the y equals, I'm going to go into the matrix menu, and I'm just going to grab A. Oh, no, I'm not. Sorry. I want to get the determinant function first. I'm going to go over to math and hit determinant. Then I'm going to go in and I'm going to go grab my A. The variable we want to use is x, so your x button right there below the mode. Let's see if I can minimize that little thing so it's not on here. Your x button, of course, is right here below the, you can't see that very well, right there below the mode. And then times, go back into your matrix menu. Number 5 there is we'll create an identity matrix of certain size. In this case, it's a 3 by 3, so I'm going to put identity 3 in there. If it were a 4 by 4, you'd put a 4 in there, and so on up the line. Okay. All right. Now that I have this typed in here, I can graph it. Hey, look at that. Looks like it crosses the x-axis at 1, 2, and 3, right? We can verify that. You let the calculator verify it for us. Above the trace button, there's a calculate button, right? Above the trace button, there's a calculate button. If I go to second calculate, number 2 is a 0 function. If you've used your 0 function before, this is probably not all news to you, but you want to enter a left bound, a right bound, and then a guess where it is. So the left bound, you need to go left of where the root is, hit enter. Right bound, do the same thing. Go right of where you think the root is, hit enter. Scroll to where you think it's close to the root, hit enter for your guess. There, it found it. It has a 0 at 1, which is what we said we had, right? You can do the exact same thing for the other 2, at 2 and at 3. This won't give you exact values unless it knows the exact values. For what I mean by that is, if you had an eigenvalue of square root of 2, it's going to find 1.414, so on, right? So if you think it might be an irrational number that you might want to check that, right? So it's like 1.4-ish, it might be root 2, 1.7-ish, it might be root 3, something like that. So it's not a perfect system because it's not going to give you exact values necessarily. But at least it's helpful. And on your final, you'll get integers. So that's always nice. Is it okay? All right. So you can do the same thing, figure out where the other 2 roots are, here and here, but you can see they're crossing at 2 and 3 anyway. But all right. Well, we can do the same thing then to find your eigenvectors. So remember to find the eigenvectors. I'll write this down, and then we'll actually find them. Remember to find your eigenvectors. There's eigenvectors associated with each of your eigenvalues. So remember, when we do that, we plug in the lambda equal to each of the values into our A minus lambda I matrix, and then find the null space of that matrix, right? Because we're trying to find the solutions to that matrix, that A minus lambda I times x equals 0. So again, the matrix was this one here that's at the top of the screen. If I plug in 1, you get 3, 0, 1, negative 2, 0, 0, negative 2, 0, 0. Right? When we plug in 1. We agree with that? Okay. Again, this is a lot of computation. At least I think it's a lot of computation. So we might as well let the calculator help us out with it. We know what the eigenvalues are. So I might as well let the calculator do the row reducing, although this one's not that hard. But I also need to change it to when I plug in a 2. I need to change it when I plug in a 3, right? So I might as well go back over to the calculator. I might as well go into matrix, math, reduced row echelon form, because I want to row reduce that thing, right? And I want to do matrix A minus, I'm going to go ahead and just type in the 1, because that's what I'll do it the other way around. I'll do minus the identity matrix, 3 by 3. And then I'm going to type in times 1, because that's the number I'm going to want to change, right? I want to do it when I plug in 1 for lambda. I want to do it when I plug in 2 for lambda. And I want to do it when I plug in 3 for lambda, right? So I'm going to put it on the end so that I can pull this back up again later and easily just change out the number. Okay. So row reduce this. There's our reduced row echelon form. If I wanted, we'll write down the answers here in a second, but let's just, because I got to flip back and forth between screens. To do the other one, if I go to second entry, if you hit second and then enter, it'll bring up the previous entry. So I can change it easily. I want to change the 1 to a 2 because that was our other eigenvalue, another eigenvalue. Do it again, hit second entry, change it to a 3. I get that one. Okay. I want to write these down on the other screen. I'm just going to switch it over real quick. All right, so for lambda equal to 1, when we did the reduced row echelon form, we got 0, 1, 0, 0, 0, 1, 0, 0, 0, right? For lambda equal to 2, the reduced row echelon form was 1, negative 2, 0, 0, 0, 1, 0, 0, 0. And when we had 3, the reduced row echelon form was 1, 0, negative 7.5, 0, 1, 6, negative 6, 0, 0, 0. I think that's a lot easier than going back in and retyping the matrix every single time and then row reducing it, isn't it? Because I have to change that lambda every single time and then row reduce. If I have it in the calculator already, that's just a super faster. All right. Now again, we want to solve the associated homogeneous systems. Let's look at the first one. Where's your free variable? In the first one here, where's the free variable? Where's the column that doesn't have a pivot? First one, right? So the first one can be anything, but what does x2 and x3 have to be? x2 is 0. x3 is 0, right? So your solutions here is anything. So I'll use a t to represent that, times 1, 0, 0 works, right? And if I go back up, if I scroll back up to the example we did, I'll scroll back down here in a second. If I scroll back up to the example we did at the beginning, that's not what I got. That's interesting. That was what we got when we row reduced it, wasn't it? Is that not what I? Oh shoot! I think I have a different matrix, don't I? I didn't actually make it. That's a different matrix. Yeah, amazing. Sorry about that. Let me try again. We're experiencing technical difficulties. Please stand by. There we go. Sorry about that. Well, then your graph probably looked different than mine too. When you graphed it. I don't know. Okay, maybe you didn't graph it. Hey, that's different. Sorry about that. That way, and then this is the other way around. Clearly, I was playing with a different matrix and forgot that I had changed it. Sorry. What's that? Yeah. All right, let me redo this. There we go. How about 0, 0.5, and then a 1 and a negative 1. My apologies. That better? That more better? Okay. All right, let me go talk back through the first one. Free variable is the second one. The first and the third are both zeros. So your eigenvector should be 0, 1, 0. Right? Because this says x1 equals 0, x3 equals 0, x2 can be anything. Yes? Yeah. I had typed in the wrong matrix into the calculator. I was working off another matrix when I was playing with another problem and forgot that I had changed it. Because I was doing this Monday and I've slept since then. So I know, isn't it amazing? All right. All right. Again, now if you go back up and compare, that was that original eigenvector that we used. The second one here, where's your free variable? Column 3. So the third entry will be a 1. The second entry is the same as the third entry, right? When I move that over to the other side. So this will also be a 1. The top one will be a negative 1/2, and that can be multiplied by anything, any scalar. Right? If I go back up, notice the matrix the vector we had before was negative 1, 2, 2. I get that vector by taking, if I can scroll that way, take that vector and multiply it by 2. And I'll get the same thing that we had before. So what we have here, and we'll write the third one down here in a second. What we have here is a basis for what we refer to as the eigenspace. This one vector generates all eigenvectors associated with lambda equal to 1. This one generates all eigenvectors associated with lambda equal to 2. So any scalar multiple works. In the last one here, again, our free variable is the third column. So the third one can be anything. The second one is the same as the third, right? And the first one is the opposite of the third. So, and then again, any multiple of that works. So again, if you were asked for a basis for the eigenspace, you would just write that one vector in a set notation, if you will. That process okay? My apologies for having the wrong matrix in it to start with. Any questions about how we did that? Notice this is all stuff we've been doing since the beginning of the semester, right? This is not new. All right. So let's talk a little bit about some properties. If you have a triangular matrix, well, when we have a triangular matrix, how do you take its determinant? If a matrix is triangular, how can you take its determinant? Yeah, just multiply the diagonal entries, right? So if you've got some triangular matrix, and just for argument's sake, doesn't matter, I'll write it as A1, A2, down AN. Let's say it's upper triangular, just for argument's sake. Okay? The argument's going to be exactly the same for if it's lower triangular or if it's diagonal. If you do A minus lambda I, you'll get those diagonal entries minus lambda down the diagonal. Doesn't change anything over here, and that's still 0 down there, right? What's going to happen when you take the determinant of that matrix? Yeah, it's just those diagonal entries multiplied by each other. Can you find the zeros of that pretty quickly? Yeah, it's already factored. What are the zeros? Yeah, A1, A2, AN, just the diagonal entries, right? Agreed? Okay. So notice that the eigenvalues here are just the entries on the main diagonal. So not a lot of work to do to find eigenvalues if you've got a triangular matrix. If it's a triangular matrix, then the diagonal entries are your eigenvalues, period. Okay. All right, let's answer the second question here. Square matrix is invertible if and only if what has to happen. All right, well, let's think about what's going to happen here. Pardon me. What is a check, a numeric check for whether or not a matrix is invertible? Yeah, the determinant is not equal to 0, right? Agreed? Okay. So if I've got this calculation, okay, if the matrix is not invertible, what would I plug in for, what's a number that we could plug in for lambda and see that numeric check for the matrix not being invertible? Okay, so let's think about a not being invertible. We know the determinant of a is 0, right? What can you plug in for lambda to see the determinant of a by itself? 0, right? So if the matrix is not invertible, then 0 is an eigenvalue, right? Because I already know if it's not invertible, its determinant is 0, right? And if I plug in 0 for lambda, I get a true statement. So 0 is an eigenvalue, right? So if the matrix is not invertible, am I going to get, if I plug in 0 here, am I going to get a true statement? If the matrix is invertible and I plug in 0 for lambda, will I get a true statement anymore? Will I get equal 0? No. So 0 can't be an eigenvalue in that case. Okay. So the theorem is that a square matrix is invertible if and only if all of its eigenvalues are non-zero. So again, let me go through the process that we just talked about. If 0 is an eigenvalue, that means determinant of a minus 0i is 0, or determinant of a is 0, so the matrix is not invertible, right? If the matrix is invertible, then I cannot get determinant of a minus 0i equals 0, because that would say determinant of a is 0, which we know it's not if it's invertible. Okay. So that argument tells us that it's invertible if and only if all the eigenvalues are non-zero. Unfortunately, I can't say much about the eigenvectors. Okay. We always have to go calculate those. All right. Here's an interesting little property. If we have an eigenvalue associated with a matrix and an associated eigenvector v, then what can we start talking about with the lambda to the k? So this is one of the reasons why we care about eigenvalues and eigenvectors. Okay? So remember that if it's an eigenvalue, we have this statement, correct? Right? That's what it means to be an eigenvalue. We can replace the matrix multiplication with the scalar multiplication, right? What if you had a squared times v? Well, what does a squared mean? What does squared mean? Multiply by itself, right? So this is the same thing as a times av. What can you replace av with? Lambda v. Where can we move that? Now lambda is just a scalar. Where can I move that lambda? Anywhere I like, right? In particular, I can put it in front if I want. What can we replace AV with? Lambda V. Okay, so now look at the equation we have. I've got matrix times V equals scalar times V. When we have that situation, what do we call the scalar with respect to the matrix? What name do we give that? Eigenvalue, right? So if lambda is an eigenvalue for A, lambda squared is an eigenvalue for A squared. Did the eigenvector change at all? It's the same eigenvector that we had, right? Think it's going to work again for A cubed? And A to the fourth. so on down the line, right? It also works for negative exponents, by the way. If your matrix is invertible, then I know that the eigenvalue is non-zero, right? So if your matrix is invertible, if you start with AV equals lambda V, I know I can do the inverse of A. I know I can do the reciprocal of lambda. And so you get 1 over lambda V equals A inverse V. It also works for negative exponents. Which is nice. All right. So the theorem is that if lambda is an eigenvalue of A with associated eigenvalue or eigenvector V, then lambda to the K is an eigenvalue for A to the K with associated eigenvector V. What this allows you to do, yeah, there's lots of things you can do. But what this allows you to do, there's things that are called stochastic processes or dynamical systems, that things change in steps, say time steps. You know what happens after 1 year, then you know say you know the probability of what happens after 1 year, and then probabilities associated with that happens after 2, then after 3, and after 4, and so on down the line. It's what's called a stochastic process. There's some other details that go into that. But you can analyze stochastic processes through matrix multiplication to go from one step to the next. An example that's referred to as a Markov chain, for example. You want to know what happens in the long run. What if there's what's referred to as a steady state solution? Right? You want to know what happens in the long run. Well, what happens in the long run is a limiting process, right? And you do that matrix multiplication over and over and over and over again. Well, instead of doing the matrix multiplication over and over and over again, what would be easier to analyze? Scalar multiplication over and over again, right? If you've done limits of scalar things, that's calculus, right? So what you're doing is changing, if you've got eigenvalues and eigenvectors for the matrix, you can change this analyzing of what happens in the long run from matrix multiplication to scalar multiplication and do limits like you do in calculus. That's one of the reasons why we care. You do some long-term analysis of things by switching from matrix multiplication to scalar multiplication. Okay. So, in any event, it's this idea that makes things nice. Okay. Notice that raising matrices to higher and higher powers does not change your eigenspaces that are associated with those original lambdas. Okay. So we'll talk a little bit more about that when we do this diagonalization stuff. All right. Let's do a slightly bigger example. But I want to just play with the calculator here with it, so that we're all on the same page with the calculator. All right, so you've got that on your papers. Let me flip over to the calculator real quick. Let's change A into a 4x4. 3, 1, -4, 0, -18, -8, 24, 0, -4, -2, 6, 0, 15, 8, -20, -1. So we've got a 4x4 matrix. What's the largest number of eigenvalues we're definitely going to see here? 4. You may see repeated ones. It's possible that, remember, you have repeated roots for a polynomial, so they see repeated eigenvalues, but we're not going to get more than 4 distinct ones. Okay? All right. If I go back over to my y equals menu, I can change that 3 to a 4. And then I can graph it to figure out what the eigenvalues are. I may have to zoom out here. Yeah, we'll have to zoom out a little bit. Looks like. There we go. 1, 2, 3, 4. We could go through and use our calculate menu to figure out what they are, but looking at where it crosses the x-axis, what do you think the eigenvalues are? Yeah, -2, -1, 1, and 2. Again, we can check this easily without actually having to do the calculate part and let the thing find those zeros. Remember, if I plug in an eigenvalue, then I have to get non-trivial solutions to the associated homogeneous system. So when I plug the eigenvalue in and row reduce, I have to see at least one free variable, period, right? So if you ever plug a thing in that you think is an eigenvalue, and you get the identity matrix when you row reduce, you calculated your eigenvalue wrong. When you row reduce, you always, always, always have to have a free variable. Okay? At least one, maybe more, but you have to have at least one. Okay. So remember, we can do that pretty quickly in here. We think that -2 is an eigenvalue, right? Notice I changed that to a 4, because it's a 4 by 4 now. We think -2 is an eigenvalue. We get a free variable, it is an eigenvalue, right? We got 0, 1/3, what is that, a 15th, I think? Maybe a 12th. A 12th? Yeah, okay. And then, so when we did that one, let me go back over real quick to the screen here. So we found, using the calculator, we got lambda 1 is -2, lambda 2 is -1, lambda 3 is 1, and lambda 4 is 2, right? We read that from the graph. Okay. So when we did lambda 1 equals -2, the reduced row echelon form was 1, 0, 0, 0, 0, 1, 0, 1/3, 0, 0, 1, 1/12, 0, 0, 0, 0. Free variable is where? Column 4. So that'll be a 1 down on the 4th component. If I have a 1, what does that make your 3rd component? The 3rd component will be -12. The 2nd component will be -1/3. And I wrote a half. And the 1st component will be 0. Good. And since I'm writing a basis, I'm just writing that one particular element, or that one vector as a basis here. Notice we're saving ourselves a lot of time with computation from having to do this by hand, aren't we? All right, let's do the next one. We said that we also suspected that -1 was an eigenvalue. So I just pulled up the old entry, put in -1. We get a free variable again in that 4th column. What are the other 3 components? 0, right? This says x1 equals 0, x2 equals 0, x3 equals 0, right? So for lambda equal to 1, if I flip back real quick, or -1, I mean, the basis for your eigenspace, we said that that last component is a 1, but the other 3 are definitely zeros. And then I forgot to close my brace off again. Okay? And again, like I said, this saves you a lot of computational stuff, doesn't it? We're doing it all on the calculator and interpreting the results we're getting from the calculator. You think you could do the last two? Okay. Same process, right? Do the exact same thing, just plug in 1 and 2. All right. So let's finish this off. You can probably already guess what our last here addition to our mega theorem is going to be. We already wrote it earlier today. Remember, our mega theorem is the set of things that statements that are equivalent to a matrix being invertible. What thing did we talk about earlier today was something being invertible? What did we say? Yeah, all the eigenvalues are non-zero. What number are we on? What is it? 27? Yeah. So 27, all the eigenvalues of A are non-zero. Lots of things being equivalent to a matrix being invertible. Might be something you want to think about paying attention to for the final. All right, so let's start talking here about the process of diagonalizing a matrix. Oops, I need to get 3 on this one. All right. So we're going to be more interested here in the actual process of what we're doing than a lot of the concepts behind it. But the idea here is that think about what we just talked about in that one result where I said that if you raise higher and higher powers of matrix, you get higher and higher powers of eigenvalue, right? But the eigenvector stays the same, right? If you've got, well, let me write it this way. Let's say you've got what we refer to as similar matrices. This is what it means to be similar. A is similar to B. If I can find an invertible matrix C, then I can write it that way. Notice that if I do powers on the right-hand side, what's going to happen in the middle? If I, let's say I square both sides here, what happens in the middle? You know, the C inverse cancels, don't they? They make the identity. So then in this inside here, I get B squared, right? Am I going to get anything different if I make it an A cubed? If I made it an A cubed instead of an A squared, what do you think is going to happen on the inside here? Get a B cubed, right? Agreed? Okay. So when you've got powers, positive integer powers on the A, and I have a matrix that's similar to it, I can just do positive integer powers on that thing that's in the middle, and then multiply by the C inverse and C on the outside. Okay. Why do I care? Well, let's think about it. When we want to diagonalize a matrix, we're looking for a diagonal matrix I guess I could have wrote my inverse on the other side. That's okay. A diagonal matrix D and an invertible matrix P. Ooh, hey. so that I can write, I do it this way, typically write it this way, A equals P D P inverse. Usually we write the inverse on the other side. This is what we mean for diagonalizing a matrix. Can't always do it, by the way. That's why we're looking for this next statement. Okay. But this is what it means by diagonalize. Why do I care? Well, when I have a diagonal matrix, how do I take the power of a diagonal matrix? Say you have 3, 0, 0, 7, and I want to take it to the 4th power. Yeah, I could just put the power on the components, right? That's it. So isn't it easier to do a power of a diagonal matrix than it is a power of an arbitrary matrix? Yeah, especially from a computational standpoint. It's a lot easier, right? So again, if I need to do an analysis of something that requires higher and higher powers of a matrix, if I can diagonalize it, it saves me a lot of time. This is why one of the reasons why we care. Okay. All right, so why do we want, or what do we have to do to diagonalize a matrix? Well, I got to find this matrix P, right? Okay. So I'm going to do this quickly since we got about we got about 1 minute now, and then we'll do some examples of how to do it. All right. It probably has something to do with eigenvalues and eigenvectors, don't you think? Okay. All right. Let's start with this equation first. This is I want to try to figure out an equation to solve where my P is on both sides, like this. Okay. Remember that if I multiply by a diagonal matrix on the right, it has the same effect as taking the first entry, multiply by the first column. Second entry, second column. Third entry, third column down the way, right? Remember when we do this has, I can think of this multiplication as take the matrix times the first column, that makes the first column. Take the matrix times the second column, that makes the second column, and so on down the line. Okay? So, if I write it this way, I would have A, say P1 down the first column, A, P2 down the second column, all the way out to A, Pn down the last column. Looking at that equation, what better the lambdas and the p's be? If I want this thing actually to be equal, what the better the lambdas and the p's be relative to A? Well, the columns have to be identical, so I would need AP1 equals lambda 1 P1. So what does lambda 1 and P1 have to be? They have to be eigenvalues and eigenvectors, right? Same thing here, eigenvalue, eigenvector, right? Okay? So this is how you're going to diagonalize and find that matrix P. Okay? You're going to calculate all your eigenvalues and then the associated eigenvectors and make that matrix. Now, I want that matrix to be invertible. So the big thing is that you have to have n linearly independent eigenvectors to be able to invert it, right? Remember that columns have to be linearly independent to be able to be invertible. Okay? So in order to diagonalize, we need to find n linearly independent eigenvectors. And we'll concentrate on how to do that next time. Okay? By the way, it's not always possible. It's entirely possible that you find a matrix that's not diagonalizable. Okay? And we'll see an example of that next time. All right. Have a good one. We'll see you on